Welcome to Senior High School Mathematics. In this presentation, let us discuss hypothesis testing, the traditional method, under statistics and probability. Here are our learning competencies. Illustrates null hypothesis, alternative hypothesis, level of significance, rejection region, and types of errors in hypothesis testing. Formulates the appropriate null and alternative hypothesis on a population mean. Before we continue, let us ponder on this. How much better is better? Suppose a school principal reads an article which states that the overall mean score for the NAT or the National Achievement Test is 78. Furthermore, suppose that for a sample of students, the average of the NAT scores in the principal's school is 82. Can the principal conclude that the students in his school scored higher than the average? At first glance, you might be inclined to say yes, since 82 is higher than 78. But recall that the means of samples vary about the population mean when samples are selected from a specific population. So the question arises, is there a real difference in the means, or is the difference simply due to chance? This time, let us proceed to some definitions. Hypothesis testing. This is a decision-making process for evaluating claims about the population. In hypothesis testing, the researcher must define the population under study, state the particular hypothesis that will be investigated, give the significance level, select a sample from the population, collect the data, perform the calculations required for the statistical test, and then reach a conclusion. Here are the steps in hypothesis testing. Every hypothesis testing situation begins with the statement of a hypothesis. A statistical hypothesis is a conjecture about a population parameter. This conjecture may or may not be true. There are two types of statistical hypotheses for each situation: the null hypothesis and the alternative hypothesis. The null hypothesis, symbolized by H sub 0, is a statistical hypothesis that states that there is no difference between a parameter and a specific value, or that there is no difference between two parameters. On the other hand, the alternative hypothesis, symbolized by H sub 1, sometimes H sub A, is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between two parameters. Let us have some examples. A medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? Since the researcher knows that the mean pulse rate of the population is 80 beats per minute, formulate the null and alternative hypothesis. Here's our suggested solution. In words, the null hypothesis may be stated that there is no significant difference in the mean pulse rate of patients after taking the new medication. In symbols, we write this as H sub 0, mu, or the population mean, is equal to 80 beats per minute, since there is no difference after taking the medication. On the other hand, the alternative hypothesis may be stated as there is significant difference in the mean pulse rate of patients after taking the new medication. In symbols, we write this as H sub 1, mu is not equal to 80 beats per minute. We write not equal since in the situation it says will the pulse rate increase, decrease, or remain unchanged. Hence, in the alternative hypothesis, we write is not equal to. We are not particular whether it is to increase or decrease. Then we write not equal to. Let us have another example. A chemist invents an additive to increase the life of an automobile battery. If the mean lifetime of the automobile battery without the additive is 36 months, formulate the null and alternative hypothesis. Here is our suggested solution. In words, we write the null hypothesis as there is no significant difference in the mean lifetime of automobile battery after using the additive. In symbols, we write H sub 0 as mu is equal to 36 months, since after adding the additive, there is no change in the lifetime of the automobile battery and it stays as 36 months. In words, the alternative hypothesis may be stated as there is significant difference in the mean lifetime of automobile battery after using the additive. Now the situation says the chemist invents the additive to increase the life of an automobile battery. Therefore, for our alternative hypothesis in symbol, we write mu is greater than 36 months. Another one. In Baguio City, a contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is 3,000 pesos, formulate the null and alternative hypothesis. In words, we write the null hypothesis as there is no significant difference in the monthly heating bills after using the special type of insulation in houses. So in symbols, mu is equal to 3,000 pesos since there is no difference. The alternative hypothesis may be stated as there is significant difference in the monthly heating bills after using the special type of insulation in houses. From the situation, the contractor wishes to lower the heating bills by using the special type of insulation. Therefore, as an alternative hypothesis in symbols, we write this as mu is less than 3,000 pesos because the contractor wishes to lower the heating bills. The null and alternative hypotheses are stated together, although in some researches, only the null hypothesis is given. The null hypothesis contains the equal sign as shown. For a two-tailed test, the null hypothesis is written as mu is equal to k and the alternative hypothesis as mu is not equal to k. So of the three examples, example number 1 is a two-tailed test. The right-tailed test states the null hypothesis as mu is equal to k and the alternative hypothesis as mu is greater than k. Of the three examples, example number 2 is a right-tailed test. In the left-tailed test, the null hypothesis is given as mu is equal to k and the alternative hypothesis as mu is less than k. Hence, the third example is a left-tailed test. The right-tailed test and left-tailed test are also called one-tailed tests. In here, k represents a specified real number. After stating the hypothesis, the researcher designs the study. The researcher selects the correct statistical test and then chooses an appropriate level of significance and formulates a plan for conducting the study. A statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected. The numerical value obtained from a statistical test is called the test value. The mean is computed for the data obtained from the sample and is compared with the population mean. Then, a decision is made to reject or not reject the null hypothesis on the basis of the value obtained from the statistical test. If the difference is significant, the null hypothesis is rejected. If it is not, then the null hypothesis is not rejected. With this, the researcher may arrive at a correct decision or commit an error. A type 1 error occurs if you reject the null hypothesis when it is true. On the other hand, a type 2 error occurs if you do not reject the null hypothesis when it is false. The level of significance is the maximum probability of committing a type 1 error. This probability is symbolized by alpha. That is, the probability of type 1 error is equal to alpha. The probability of a type 2 error is symbolized by beta. That is, the probability of type 2 error is equal to beta. In most hypothesis testing situations, beta cannot be easily computed. However, alpha and beta are related in that decreasing one increases the other. Statisticians generally agree on using three arbitrary significance levels: the 0.1, 0.05, and 0.01 levels. That is, if the null hypothesis is rejected, the probability of type 1 error will be 10%, 5%, or 1%, depending on which level of significance is used. When alpha is equal to 0.1 or 0.10, there is a 10% chance of rejecting a true null hypothesis. When alpha is equal to 0.05, there is a 5% chance of rejecting a true null hypothesis. And when alpha is equal to 0.01, there is a 1% chance of rejecting a true null hypothesis. The critical value separates the critical region from the non-critical region. The symbol for critical value is CV. The critical or rejection region is the range of values of the test value that indicates that there is a significant difference and that the null hypothesis should be rejected. The critical value can be on the right-hand side or on the left-hand side of the mean. For a one-tailed test, its location depends on the inequality sign of the alternative hypothesis. The non-critical or non-rejection region is the range of values of the test value that indicates that the difference was probably due to chance and that the null hypothesis should not be rejected. In example 2, where the chemist is interested in increasing the average lifetime of automobile batteries, the alternative hypothesis mu is greater than 36 months. Since the inequality sign is greater than, the null hypothesis will be rejected only when the sample mean is significantly greater than 36 months. A one-tailed test indicates that the null hypothesis should be rejected when the test value is in the critical region on one side of the mean. A one-tailed test is either a right-tailed test or left-tailed test, depending on the direction of the inequality of the alternative hypothesis. This time, let us have finding the critical values for specific alpha values using the standard normal distribution, or what we call the Z distribution table. Step 1. Draw the figure and indicate the appropriate area. If the test is right-tailed, the critical region with an area equal to alpha will be on the right side of the mean. For a right-tailed test, use the Z value that corresponds to the area equivalent to 1 minus alpha. Let us have an example. Find the critical value for alpha equal to 0.01 in a right-tailed test. So for step 1, we draw the figure, and since this is a right-tailed test, the critical value and the critical region is to the right of the mean. The area to the right of the critical value will be 0.01 since alpha is equal to 0.01. Using table E, we know that the area is to the left of the Z value or any Z value by default. Hence, the area to the left of the critical value is 1 minus 0.01, and that is 0.9900. This is what we're going to look for in the table E or the Z distribution table. The closest to that value is 0.9901, and the value on the first column is 2.3. On the first row is 0.03. Therefore, the critical value for alpha 0.01 in a right-tailed test is 2.33. This time, let us show the critical and non-critical regions for alpha is equal to 0.01 in a right-tailed test. In the previous slide, we were able to identify the critical value as 2.33. And this, as we know, separates the critical and the non-critical region. Since alpha is equal to 0.01, the critical region has an area of 0.01. And the non-critical region is 1 minus alpha, that is 0.9900. The critical or rejection region is the range of values of the test value that indicates that there is a significant difference and that the null hypothesis should be rejected. The non-critical or non-rejection region is the range of values of the test value that indicates that the difference was probably due to chance and that the null hypothesis should not be rejected. If the test is left-tailed, we still follow step 1, but the critical region with an area equal to alpha will be on the left side of the mean. For a left-tailed test, use the Z value that corresponds to the area equivalent to alpha in the standard normal distribution table. For the critical and non-critical regions for alpha is equal to 0.01 in a left-tailed test, we have the critical value for Z to the left of the mean, that is negative 2.33 for alpha equal to 0.01. Then the area to the right of the critical value will be 0.9900. The critical region is to the left of the Z value or the critical Z value, and the non-critical region will be to the right of the critical Z value. If the test is two-tailed, alpha must be divided by 2. 1/2 of the area will be to the right of the mean, and 1/2 will be to the left of the mean. Step 2, for a two-tailed test, use the Z value that corresponds to alpha over 2. For the left value, it will be negative. For the right value, use the z value that corresponds to the area equivalent to 1 minus alpha over 2. It will be positive. Let us have an example. And the critical values for alpha is equal to 0.01 in a two-tailed test. Then identify the critical and non-critical regions. Step 1, we draw the figure and we divide alpha equals 0.01 by 2. Then we have 0.0050 to the left and to the right of the mean. Then the area between these two values will be 0.9900. Looking for the critical value using the standard normal distribution, we have the closest value as 0.9951, and that will be 2.5 on the first column, 0.08 on the first row. Therefore, the critical values will be positive, negative 2.58. The critical and non-critical regions, we have already identified the z critical values as negative 2.58 to the left of the mean and positive 2.58 to the right of the mean. The critical regions have area 0.0050 to the left and to the right of the mean. Therefore, the non-critical region has an area of 0.9900. This time, let us have some practice exercises. In the practice exercises, you will be given 15 seconds to pause the video and answer. Play it again when you are ready to check your answer for each item. Using the standard normal distribution table, find the critical values for each situation and draw the appropriate figure showing the critical region. Letter A, a left-tailed test with alpha equal to 0.10. Go. Time is up. Let us show the answer. For step 1, draw the figure. Since this is a left-tailed test, the z critical will be to the left of the mean, and the area to the left of that z critical value will be equal to alpha, and that is 0.10. Using the standard normal distribution, we look for the area 0.1000, and the closest value is 0.1003. On the first column, we have negative 1.2, and on the first row, we have 0.08. Then the critical value is negative 1.28. The critical region will be the region to the left of the z critical, and we have the area 0.1000. To the right of the z critical is the non-critical region. Letter B, a two-tailed test with alpha equal to 0.02. Go. Time is up. Let us answer. First, we draw the figure and divide alpha into 2 since this is two-tailed test. So we have 0.02 divided by 2. We have 0.0100 to the left and to the right of the mean. To find the critical values, we can either use 0.0100 or 0.9900 since 1 minus 0.0100 is 0.9900. Then we use the standard normal distribution table to find Z critical. The closest to that again is 0.9901, and that is 2.33. So we have the critical values for Z as negative 2.33 or positive 2.33. Then we have the critical regions, one to the left of negative 2.33 and the other one to the right of Z equals 2.33. Letter C, a right-tailed test with alpha equal to 0.005. Go. Time's up. Let us show the answer. First, let us draw the figure, and since this is a right-tailed test, we have the Z critical to the right of the mean, and the area to the right of that Z critical is 0.0050. Using the standard normal distribution table, we look for the area 1 minus 0.0050, and that is 0.9950. The closest to that is 0.9951, and the Z value is 2.58. Hence, the critical region is to the right of that Z critical value, 2.58. In the next presentation, we will discuss Z-test for the mean. That will be all. Thank you for watching. Please subscribe for more of math lessons.